All right, in this video, we're going to talk about radioactive decay with regards to half-life. Now, half-life is the time it takes for half the material in a radioactive sample to decay so that it is went from unstable to being a stable state. And so basically half the material remains unstable, half the material becomes a stable form, and typically it is a different element. So make sure you refer back to other videos that I have on artificial and natural transmutation, talking about things like alpha decay and beta decay. And so I have a couple different examples here. And obviously with New York State, use your table N. Table N has the selective radioisotopes, and the second column talks about the time length or the half-life of a specific material. So for example, it says how much of an original sample of 137, this is a CS, 137 cesium remains after 90.6 years. So what we need to do anytime we are dealing with half-life questions, we need to figure out how many half-life cycles has actually occurred, or how many half-lives they've actually gone through. So the total time here is 90.6 years. According to the chart, cesium-137 is about the fifth one down, has a half-life of 30.2 years. So the half-life is 30.2 years. I know the total time is 90.6, the half-life is 30.2 years. What we can do is take 90.6, divide it by 30.2, and we end up with 3x, or basically just 3, okay? 90.6 divided by 30.2, 3 times. That means it's gone through 3 cycles or 3 half-lives. So I want to know how much of an original sample. We'll talk about with masses. Sometimes the state asks you in percentages. Sometimes New York State asks you in fractions. So for example, if I started out with one whole object, I know after one cycle, I am down to a half. After another cycle, a half is a quarter. And then my third cycle, I am down to 1/8. So be careful with what the state is asking you. Obviously, we're always starting out with a whole number. This could have been 100%, down to 50% after one cycle, down to 25% after 2 cycles, and down to 12.5% after 3 cycles. So depending on the way that they're expressing the question, 1/8 or 12.5%, it really means the same exact thing. Now, on the other hand, they might have given you a starting mass, and it could have said, you know, how much of an original sample weighing 20 grams would remain after 90.6 years. They could have thrown that in there. So we're going to do the same thing, but instead of starting with 1 as a whole number or 100%, we're going to start with 20 grams. So 20 grams every 30 years. So 30 years later, one cycle later, it's down to 10 grams. 30 years later, it's down to 5 grams. And then finally, the third cycle, 30 more years later, or 30.2 to be specific, down to 2.5 grams. So all 3 of those could be possible answers when you're looking for the type of math that the state's asking you when you're doing your half-life decay curves. So again, the big thing is to always figure out the total number of trials or half-lives first, then start cutting it in half that many times. Now, one of the things I want to point out, this first number, the 100%, the 1, that number does not count. That number is very important because you're starting with that number, but that does not count. What counts is the number of arrows or number of values you have after that. So 1/2, a quarter, 1/8, there's my third one. 50%, 25, 12.5, there's my third one. 10, 5, 2.5, there's my third one. The key thing is how many arrows or how many new numbers do you have after that. That's what you're looking for your answer. Now, as far as the curves go, I'm going to do a generic one over here to the side, but all of the curves, if you plot any of these into any curve or into any graph, they should always have the same exact trend. And one of the examples I'm going to use is a sample of radon. Now, I'm going to round up radon. Radon, according to the chart, is, I believe, 3.8 days. So it's about 2/3 of the way down is radon when you're looking at that. And 3.8 days, I'm going to round it up to 4 days because I've just spaced out as easy as I could. So 4, 8, 12, 16, 20. Let's say we start out. Let's say in the very beginning, we have a 60-gram sample of radon. 4 days later, that is going to cut in half. Okay, so I'm going to go 4 days up, half of the material will decay, because that is what half-life is all about. It's the amount of time it takes for half the material to decay. So half the particles, or half the atoms, decayed. So with the 30, half of that 4 days later will also decay as well. So about 15. I'm going to estimate here in between. So 4 days later, we're about halfway between 20 and 10. Another 4 days later, I'm going to take 15, cut that in half to 7.5. We're going to be somewhere down here. My numbers aren't going to be perfect. 7.5, half of that, and we're going to get to about 3. So now I'm getting really close to the bottom. And then it's going to approach 0, and it's going to continue to get harder to map it out. But what I want to point out is the curve and the shape of the curve. It downwardly approaches 0, and it curves, but never really gets there. Okay, and my curve isn't perfect, but it's never really going to get to 0. Now, what we have to think about, even if I had 1/100th of a gram, something, 10th, 100th position, that's something we can very, with major difficulty, we can hardly weigh that in a high school setting. Okay, if you are in a college laboratory, maybe you have one of those really fancy scales that actually has, the boxes on it, and it prevents any current, and it is a lot more calibrated to do maybe into the 1,000th position, or maybe even the 10,000th position. But I want you to think about what you've learned all year with the size of atoms. Even if I have something that is, in the 1,000th or 10,000ths of grams, you're talking still an immense amount of atoms that can still exist. And so, for the sake of the curve, it gets down to about 0, where you're not really going to see it. And over time, it gets to a point where it's negligible, where we basically say that it doesn't exist anymore. Now, these charts can also be used to determine other things. It could be used to determine perhaps how long something is decayed if I know a percentage, or if I know an amount. So let's say we're talking about carbon-14 dating. Instead of 4, 8, and 12, we could turn these into years. And if we average this out, I'm going to change this. And for the half-life of carbon, we're going to round up as well. Carbon is about 5,700 years. We're going to make it a little easier. We'll call it 6,000 years. So there's 6,000, there's 12,000, 18,000, 24,000, and 30,000 years. So after 30,000 years, there's almost hardly any carbon left, because this would plot the same exact way. If I started with 60 grams of carbon, after 6,000 years, I'm about 30 left. If I'm at 12,000 years, I'm about 15. So let's say, for example, they find a carbon sample, or a sample of something, and they know the proportions. They know what percentage it is of carbon and what other percentage it is of other elements. What they can do is they can map that on the chart. So obviously up here, this is 100%. This would be 50% of that element. This would be 25% of the element. Next step, 12.5%. That one right here would be 6.25%. Get rid of the decimal. And then we got 3.6%. Sorry, do my math wrong. 3.1 and change. And it keeps getting smaller and smaller and smaller. Just trying to do this off the cuff here. So if they were to find a material, let's say they find some relic, or they find something that's buried in the ground, and they want to know how old it is, they can take a sample of it. Obviously, they put it into a certain machine. They could spit out what its chemical composition is. And if they knew the percentages of, for example, carbon to other elements, they might say, oh, it's 12% carbon. So if it's 12% carbon, maybe it's right here, right below the 12 line. Maybe they'll estimate that it's about 18,500 years old. Okay, so they're going to be able to do something known as, in what you learn in earth science, is possibly the difference between absolute and relative dating. Relative dating is where you looked at different layers, and things that were on top of other layers were younger, things that were below were older. Okay, so that was called relative dating. They were relative to each other. Absolute dating is something that takes place here. You're actually going to get an actual accurate time frame, within possibly years, or within a couple hundred years. That's going to be a lot different than when you think about your earth science, when you're talking about eras and epochs and things like that might have been millennia and thousands of years in time. So they can map this out. So there's a very good benefit to the half-life curve. Main thing again I want to point out is all half-life curves have this general indirect relationship, okay? As time goes up, the concentration goes down. And every single time it cuts in half, cuts in half, cuts in half, cuts in half. And that is the basis, behind half-life. If you have any questions, feel free to leave them below. Obviously hit up your chemistry teacher. But again, if you want any extra help, feel free to check out the videos. Make sure you subscribe to the channel and you can hear about all different aspects of high school related chemistry. Thanks.